Alright, welcome back, and we are going to be diving into some great units here as we move forward. As you can see here, we are going to be looking at naming ionic compounds. We have in the past videos laid a fantastic foundation for you now to build upon. You've learned about atoms and subatomic particles. You've learned about the electrons, ions, isotopes. You've learned about the electron configuration, which is crucial understanding why the periodic table is arranged the way that it is, and why everything in a group, in a column, a family, have similar properties, chemical properties, and physical properties. So now we have that foundation. We're going to build upon that, and we're going to be talking about naming compounds. We're going to be talking about reactions. We're going to be talking about balancing reactions. And this is really some of the neat stuff in chemistry that you're going to be learning as we move forward. So let's dive in and let's look at naming ionic compounds. We're going to be answering this question: what are the structural units that make up ionic compounds and how are they named? Now, this particular video is specifically talking about ionic compounds. So we're going to talk about ionic compounds, and we're going to be talking about covalently bonded compounds. So just keep that in mind. There are two separate ways to name things, and today, in this video, we're going to be looking at ionic compounds, which I'll explain how you can identify very easily and quickly what is an ionic compound. So it's often convenient to write a chemical symbol, and you're familiar with those chemical symbols on the periodic table. All right, we might write down the substance table salt as NaCl, and the name for that is sodium chloride, which you're going to learn about today. And it can be a bit tacky to say NaCl. In other words, just to pronounce the letters as they appear in our symbols. So we are going to be using the names and a proper naming system for these ionic compounds. So we want to learn how to properly name these ionic substances. In Model 1, we are given kind of a condensed version of the periodic table. This is not the complete periodic table, and it is showing you a selection of different ions. Remember, an ion is an atom or a group of atoms of, let's say, an atom of an element or a group of atoms that has a charge, either positive or negative charge. Why does it have a charge? Because it has either fewer electrons than the total number of protons, or it has more total electrons than the number of protons. So either way, it's going to give it either a positive if it has more protons than electrons, or a negative if it has more electrons than protons charge on that particle. So we see here that in this first group, all of these particular elements, those atoms are going to form +1 ions. These form +2. Here, if we skip over the transition elements, we've got +3 for aluminum. And then if you skip away to the other side, ignore the noble gases for a second. But this first group, the first one to the right, that is, this is your halogens, and they all form ions of -1. Oxygen group is -2. Nitrogen group is -3. And then you'll notice that this group in the middle has some variance. Okay, so those are the transition elements. So let's just, having set up this model, let's now go through and answer some of these questions, and it'll help us develop our understanding of naming ionic compounds. So identify 3 elements that form only one cation. Cation is positive ions. So we're looking at positive. Notice positive are all over here on the left side of the periodic table. These are metals. Metals are on the left side of your periodic table. All of these on the right side, these are non-metals. Keep that in mind. 3 elements that form only one cation. Well, any one of these right here. Group 1 and Group 2, you could also mention aluminum and zinc and silver. Those are some of the elements that you should definitely understand as far as what ion they form. Always, Group 1 is always going to form +1 ions. Group 2 is always going to form +2 ions. And then if you come over here, this would make sense if you jump over the transition elements. This would be +3, and then count diagonally. Aluminum is +3, zinc is +2, silver is +1. Those you should know. You should just understand how to find the charges on those ions because they never change. They are always going to be the same. Group 1 +1, group 2 +2, aluminum +3, zinc +2, silver +1. Okay, so you can name any one of those that we just talked about. Identify 3 elements that form only one anion. Anion is a negatively charged particle. So over here, you could name any one of these on the right side of the periodic table. These are all nonmetals, and those always form the same charge on their ions. This halogen group right here, always -1. Oxygen group, always -2. Nitrogen group, always -3. Identify 3 elements that form more than one cation. Remember, cation is positive. So that would be anything in this middle section. These are often called the transition elements or transition metals. So iron, nickel, copper, mercury, tin, lead. Okay? The reason why, by the way, these transition elements, remember you are starting to fill the d orbitals, and the d orbitals are at a similar energy level as your s and p. So sometimes there are electrons that are pulled from the d orbitals as well as the s. This is your s block. Remember, the s orbitals or the p orbitals. Given these transition elements, multiple ions that could form. Okay, so it might lose 2 electrons. It might lose 3 electrons. It might lose 1 electron. It might lose 2 electrons. That's why these transition elements, metals in the middle here, often have multiple ions that form. In what region of the periodic table are these multiple ion elements usually located? And that would be in the middle. Those are your transition elements or transition metals. Consider the ions of potassium and sulfur. So potassium over here, sulfur over here. Write chemical formulas for all possible ionic compounds involving these ions using the simplest ratio of potassium and sulfur. Keep in mind that the sum of the charges in an ionic compound must equal 0. Here's what they mean. If potassium and sulfur were to combine to form an ionic compound, here's what happens. Potassium, sulfur, if they're neutral atoms and they bump into each other, potassium has the tendency, because its electron configuration ends in, remember from the previous video, we are in the 4th period here, potassium, so it's going to end in 4s1. It's in the first group, the s block, 4th column. The sulfur over here, it is in the p block, and it is in the 3rd row. It's going to end in 3p, and this would be 1, 2, 3, 4. It is 4 into 4 deep in the p block. So 3p4. So here's what potassium is thinking. Potassium is thinking, I have this 1 electron right there in the 4th energy level, and it is requiring me a lot of energy to maintain that 1 electron in that 4th energy level. If I could get rid of it, I would be at a lower energy level, and I would be more stable. But it needs somebody to take the electron. It just can't just get rid of it. Okay? Sulfur is thinking, I've got these 4 electrons here in the 3rd energy level. Either I get rid of them, that's a lot of work to pull away all those electrons, or I want to add 2 more to make the 3rd energy level full like the noble gases and have this a 3p6 kind of configuration. It doesn't turn into a noble gas. I'm just saying if I could add 2 more electrons, if I could get 2 more electrons here, then this 3rd energy level will be full. I would have 3p6. That's a full p sublevel, more stable. So it wants to add 2, potassium wants to lose 1, and those are the ions that they like to form so they can be more stable. That's the whole reason why elements form compounds, because together the compound is more stable than the elements or the atoms individually. So potassium would like to get rid of its electron. Sulfur would like to pick up 2. Well, there's only one way that's going to happen. Potassium is going to have to bring a buddy, and that buddy is going to also lose 1 electron. Together, these 2 potassiums are each going to lose an electron and hand it over to sulfur. Sulfur then has become a 2 negative charged ion. Each potassium is a +1, and these 3 particles are all going to form a compound, and that compound would be 2 potassiums. This is how we write it: K with a subscript of 2 and then 1s. That means 2 potassium atoms are bonded to a sulfur so that you have a neutral compound. The total charge on this has to be 0. Total charge has to be neutral. Okay? So you've got a plus and a plus from the 2 potassiums and a -2. Well, 1 + 1 and +1 added to a -2, that's a total of 0. So whenever you combine ions, they're always going to combine in a ratio to give you a neutral charge on that compound. So you always are guaranteed, always, always, always guaranteed that there is one set ratio for ions to combine. Metal and nonmetal. Always metal and nonmetal for an ionic compound, because you have to have cations, those are metals, and anions, those are nonmetals. So you have to have metal and nonmetal to form an ionic compound. And they always are going to form that ionic compound in a particular ratio. Always, always, always. So, this is the only possibility for potassium and sulfur to combine. That's it. Consider the ions of iron and sulfur. Write chemical formulas for all possible ionic compounds involving these ions using the simplest ratio of iron and sulfur. Keep in mind again that they must combine so that charges are 0. Here's the difference now. Iron, you've got 2 options. Is it iron 2+ or iron 3+? Well, we're going to look at both and write the possible compounds. So if you have iron and you've got sulfur, and let's say iron, it can lose 2 electrons or it can lose 3 electrons. It can do either one. So it can form an iron 2+ ion. That's 1 iron atom losing 2 electrons to give it a charge of +2. Or iron has also the ability, 1 iron atom could lose 3 electrons and become a charged particle of 3+. Sulfur only has one option. It will always gain 2 electrons. Okay? So if this particular iron atom, which lost 2 electrons, is going to be attracted and bonded to the sulfur, which gained 2, this iron donated its 2 electrons to the sulfur, and then you've got positive and negative ions. Those charges are going to be attracted to each other, forming your ionic compound. So this is going to result in iron, 1 iron ion, remember 2+, and 1 sulfur ion, 2 negative, coming together to form a single ionic compound. You no longer write the ion charges on the compound formula. You don't need them anymore. This is no longer a charged particle. It is a neutral compound. Individually, those atoms are going to be charged. That's when they're ions. But when they come together and form a bond, you no longer write the charges on the Fe or the S. It is a total charge of 0, combined charge. Now let's say sulfur and iron 3+ run into each other. Let's say that this iron here, this particular iron atom wants to lose 3 electrons, but the sulfur only wants to gain 2. Well, they're going to have to call in some buddies then, okay? So iron says, okay, well, I'll bring in a buddy. It will donate 3 as well. This sulfur says, well, I've got a buddy, and it wants 2. Well, iron's saying that's not enough. We've got 6. We've got 6 total electrons that we're willing to donate. These 2 sulfurs are willing to take 4. So sulfur's going to have to bring in another buddy. So this is the combination that we must combine in order to get a neutral compound. You're going to need 2 iron 3 pluses to combine with 3 sulfurs. So this would be iron 2 Fe2S3. Okay? So the point here is that when you've got multiple ions, there are 2 or maybe 3 different possible formulas for iron sulfur, or iron sulfide, as you'll see the naming in a little bit, iron sulfur. So we're going to have to make sure we know the difference between those two when we name them, and you'll see how we do that in a little bit. Okay? Here's a little trick for understanding how we're going to get these subscripts, by the way. All right? If we look at iron 2 plus and sulfur 2 negative, you ignore the plus and negative, or the plus and minus, and you take the magnitude of the charge and make that the subscript of the opposite element. So this would be Fe2S2, but then you always simplify that. Well, if they're both 2, you can simplify that to it's a 1-to-1 ratio, so it's FeS2. Same thing with the iron 3 plus and the sulfur 2 negative. You look at the magnitude of their charges. Iron is 3, sulfur is 2. I know they're plus and negative, but don't worry about that. This 2 here would become the subscript for the iron. This 3 here would become the subscript for the sulfur, and that's how you know you would have iron 2, Fe2, and S3. Okay? And that's the simplest the ratios you can get there. All right, model 2. Let's look at the names now. We looked at kind of how we form the formula, but let's look at the naming of it. And these are all ionic compounds, metals that are forming only one ion. So these are ionic compounds with metals that only form one ion. Sodium always forms Na+. Calcium is always a Ca2+. Silver is always a +1. So what they're saying is all of these metals that are involved here, zinc, aluminum, and strontium, are always going to form the same charge on their ion. Not all of them the same. I mean, they don't have multiple options is what I'm saying. Circle the symbol for the metal in each of the compounds. So sodium, calcium, silver, zinc, aluminum, and strontium. Those are your metals. The metal always comes first in the ionic compound formula. The non-metal is always second. Which element comes first? There you go. And it is the metal. Okay? Therefore, the non-metal second. Use the table of ions in Model 1 to answer the following questions. In the compound zinc phosphide, what is the charge of the zinc ion? Well, zinc is always +2. Okay? And in that same one, what is the charge of the phosphide ion? Phosphide is a 3 negative. How do I know that, by the way, just by looking? Well, when I look up here at zinc phosphide, notice the ending, by the way, we'll talk about that. Zinc phosphide, Zn, I need 3 Zns. I need 3 Zns, 3 zincs, to combine with just 2 phosphide ions, 2 phosphorus ions. Okay? Well, that must mean in order to get neutrality out of this, make sure this is all neutral, if I look at the possibilities here, 3 and 2, that must mean each one of these is a -3, and each one of these is a +2. That's how they're going to combine to make sure I get a total of +6 and -6 gives me 0. So I can, just by looking at the formula, I can figure out what the charges are on these particular ions if they were separated, just by knowing a few of the metal ones, the metal ions that never change. Zinc is always +2, then I know I can figure out the phosphide ion. Okay? A 3-to-2 ratio of ions is necessary because you always want to make sure that the total charge on your compound has to equal 0. It must equal 0. The compound carbon dioxide has a name that gives you a hint as to how many oxygen atoms are in the compound. Is there anything in the name zinc phosphide that indicates there are 3 zinc and 2 phosphorus ions in the formula. No. What they're saying here is later on we're going to talk about covalent compounds, covalent molecules, and this is a nonmetal and a nonmetal. So this is carbon, which is a nonmetal, oxygen, a nonmetal, and that di right there is a prefix telling us that carbon and oxygen are going to be in the ratio of carbon and 2 oxygens. The di is for 2 there. It's telling us how many of each. That is not the case. You never write prefixes. Never, never, never write prefixes for ionic compounds. How do you know it's an ionic compound? Metal, nonmetal. Starts with a metal. Second part is always going to be nonmetal, or a polyatomic ion, which is usually nonmetals. Okay? Metal, nonmetal. So how do we know the ratio in which they're going to combine? Charges. Ionic compounds, you have to know the charges of these ions that are coming together. That's how you know the ratio. The charges have to dictate how many of each are going to come together to form a total charge on that compound of 0. So that's why I know zinc phosphide. I don't need to have any prefixes for zinc phosphide because I know zinc is a +2 and phosphorus is a -3. So I need 3 zinc and 2 phosphorus to make my compound neutral, and the name of it is going to be zinc phosphide. Is there any other ratio of zinc and phosphorus ions that could exist? Could you have Zn2p or Znp2? No, you can't. Remember, we're always simplifying this. So this is the only ratio in the simplest. Yes, you could write Zn6p4, but that's the same ratio as 3:2. Okay, we don't write larger ratios that are equal. We write the simplest ratio. So none of these will not work because those will not give you a neutral compound. Number 10 says, explain why you don't need to specify the number of ions. You don't need to specify the number of ions because the charges determine number of ions that combine. Remember to give you a total charge of 0. Model 2 is labeled metals that form 1 ion. Okay, we've kept it simple so far. This is just for 1 ion. What other metals that form only 1 ion could be included in Model 2 list? So other metals that only form 1 ion, well, anything, if you go back up to Model 1, you'll notice here, any one of these, as well as aluminum, zinc, and silver, always have a single option for what ion is formed. So any of those, you are guaranteed that you can figure out in what ratio would they combine with any of these nonmetals here. Okay? Describe how the names of the nonmetal atoms are changed when they are in their anion form. Okay, so if you take oxygen, all right, oxygen, and it becomes an ion. Oxygen is always going to want to gain 2 electrons to form an ion. It always wants to gain 2 electrons. It will become more stable if it's able to gain 2 electrons from some metal. Metals readily give up electrons. Non-metals like to gain electrons. So if oxygen can gain 2 electrons, it'll become more stable, and it'll become a charged particle, and then it's going to be attracted to any metal that has a positive charge on it. Well, oxygen, when we say oxygen, we're talking about oxygen, usually it's diatomic, O2, but if it's an ion, we then change the ending so that we know it's an ion, and it is called ox, and the ending is IDE. So you change the ending always to IDE for a non-metal ion, and that is always the second part of the name. So that's why you see up here it was called zinc phosphide. The phosphide ion is from phosphorus. Okay? So name the following ionic compounds using what you learned. So all I have to do is, I see this is a metal, nonmetal, metal, nonmetal, metal, nonmetal, metal, nonmetal. All of these are ionic compounds. Guaranteed. Therefore, I don't need any prefixes. I don't use prefixes. I don't need them because these are always going to combine in a set ratio. Always. It's always going to be Li2O. Why? Because Li, lithium, always forms a +1 ion. Oxygen always forms a 2 negative. That's why it has to be 2 lithium ions combining with the 1 oxygen to form lithium. And then oxygen, but change the ending to oxide. Magnesium fluoride. Why is it MgF2? Because Mg, magnesium, always forms a +2. Fluoride always forms a -1. Actually, you write the 1 and then the negative. And so I'm going to need 2 fluoride ions with the 1 magnesium to make a neutral compound. They're going to come together as MgF2. Remember, no charge is written on the compound, only if they're individual ions. This is neutral. MgF2 is neutral. The name of that is magnesium fluoride. Here we have aluminum sulfide and potassium nitride. Nitride. Okay? Provide the chemical formula for each of the following ionic compounds. Okay, now we have the name and we need to write the formula. So barium is in group 2. I know it's always going to form a +2 ion. Chloride is in the halogens, and that's always going to form a -1. So I need 2 chloride ions for every 1 barium. BaCl2. Magnesium oxide. Magnesium is always a +2. It is in group 2. Oxygen, oxide ion, is always going to be a -2. I need 1 of each. So that's just going to be MgO. Consider the 2 chemical formulas you wrote in question 3 for compounds of iron and sulfur. Would the name iron sulfide be sufficient to uniquely identify either of these compounds? Okay, so remember we had, back up above there, we had Fe2 plus combining with sulfur, and we had Fe3 plus combining with sulfur. Iron can form multiple ions. This one, they are going to form a compound in a 1-to-1 ratio. This one is going to form a compound in a 2-to-3 ratio. So we cannot just say iron sulfide. Because which one are we talking about? Are we talking about the FeS or Fe2S3? Which one is it? So now we have to, when we've got multiple ions for metals, we have to add one little extra thing to make sure that we distinguish between, is it iron sulfide with the iron 2 plus ion, or is it iron sulfide with the iron 3 plus ion? Which one is it? So here's the key, here's a little trick. Let's look here. We've got copper and oxygen. We've got tin and fluoride. We've got lead and oxygen. We've got iron and chloride. Notice we've got 2 here that have copper and oxygen. We've got 2 that have tin and fluoride. We've got 2 that have lead and oxygen. We've got 2 that have iron and chloride. And you may notice right away, what's the difference in these names? Oh, we've got Roman numerals. That's going to help us. Model 3 is labeled metals that form multiple ions. Remember, those are the transition metals. What other metals that form multiple ions could be included in Model 3? Well, any of those transition metals, if we scroll back up here, any of these transition metals here in this central region, excluding silver, zinc, and aluminum, those are going to have multiple possible ions. So you're going to have to use Roman numerals when you come across those. That's why I suggested you memorize always that group 1, group 2, and then aluminum, zinc, and silver always have the same ion charge. All the others are multiple ones. All right. Describe the most obvious difference between the names in Model 3 and those in Model 2. The obvious difference is the Roman numeral. We've got Roman numerals now to make sure we know, is it copper plus 1 or copper plus 2? Is it tin plus 2 or tin plus 4? Which one are we using? Which of the metal ions are we using? Roman numerals, Roman numbers, okay? Do the Roman numerals in the names of Model 3 relate to the number of cations or number of anions in the formula unit? All right, support your answer by citing two specific examples. Okay, what this is actually telling you, it is telling you the number of the charge on the cation. And it also is going to tell you then how many of the non-metal ions you need. So let's break this down a little bit. Let's look at these two copper compounds. We've got copper and we've got oxygen. Well, copper can form a +1 ion or it can form a +2 ion. So that's going to, influence in what ratio it combines with oxygen. So if it's a +1, oxygen always forms a -2. So if it is a +1 copper, you're going to need 2 coppers to combine with the 1 oxygen to make a neutral ionic compound. So this formula here is going to be these two combined to give me copper 2, Cu2, and an O. Alright? And here, they're going to combine in a 1-to-1 ratio, because a +2 and a -2 gives me 0, so this is just Cu and O. I need to know the difference between these. I can't name both of them copper oxide. I'm going to get confused. I don't know which one you're talking about. So, you need to name them differently. And the way you do that is by naming them copper. What was the charge on this copper? It was +1. So the Roman numeral tells me the charge on the copper. Copper 1 oxide. What copper ion did I use over here? I used the one with the +2 charge on it. So this is copper 2 oxide. And it just so happens that that Roman numeral, it doesn't just happen, but I mean, you know that the charge on the one gives you the subscript of the other, and vice versa. So this charge, copper 1, is a charge of 1. That tells you what's going to be the subscript for the oxygen. Okay, that's why it's a 1 on the oxygen. Copper 2 tells you that it's going to be a subscript on the oxygen as of 2, but that's also going to be for the copper, so it's going to be a 1-to-1 ratio. But what my point here is that this Roman numeral is telling you the charge on the metal. Okay, it's telling you the charge on the metal. This is a copper 2. This is a copper 1 that is being in this formula, that's being used in the formula. Okay? Alright. Keeping in mind that the sum of the charges of an ionic compound must always equal 0. Key, this is very, very important. Use the chemical formulas in Model 3 to answer the following questions. Identify the charge of the copper cations in copper 1 oxide. If it's copper 1 oxide, then the copper has a +1 charge. Copper 2 oxide, then the copper has a +2 charge. That Roman numeral is telling you the charge on the metal. Identify the charge of the iron cations in iron 2 and iron 3. Well, this one here, it must be using iron 2+ ion. This is using iron 3+ ion. Okay? Roman numerals are telling us what? The charge on the metal ion. Okay? Fill in the table below using what we've learned. So, if we have this formula, lead chloride, I look at this right here, I know chloride is always a -1. Always. So if I need 4 of them, that must mean the lead has a +4 charge, so the name of it is going to be lead 4 chloride. I look here, oxygen is always a -2, and if I need 2 irons, that must mean, this is where you can use these subscripts here and go to the other element. If oxygen is a -2, iron must have a charge of -3, or sorry, +3. And so this would be iron 3 oxide. Oxygen is always a -2, so this tin must also be, or not also, but must have a +2 to give you a total charge on the compound of 0. So this must be tin 2+. We have to put that because tin has multiple ions that are possible. So we say tin 2 oxide. Copper, and the Br here, bromine is always a -1, and it requires 2 of them here, so this copper must be a +2. So this is copper 2 oxide. All right. For each of the compounds in the table below, determine the type of metal in the compound and then name the compound using the correct naming method. So, what you must do first for ionic compounds, well, first you have to identify, is it an ionic compound? Does it have a metal and a nonmetal? Metal and nonmetal. If it does, it's ionic. And we're going to use this naming system that we're talking about in this video. Don't use prefixes for ionic compounds. That's coming up later. Once you've identified it to be an ionic compound, then we have to determine the metal that is involved. Does it have only one possible ion, or does it have multiple ones? That's why I told you you must memorize and understand that group 1, group 2, aluminum, zinc, and silver always have the same ion charge. Group 1 is always a +1. Group 2 is always a +2. Aluminum +3, zinc +2, silver +1. Those are the ones you should know. Everything else, for the most part, I'm pretty sure is multiple, okay? Calcium, I know, I've memorized it, it's a +2. So metals forms only one ion, yes, it is calcium 2+. Let's just go through all the metals first and then we'll name it. Magnesium, yes, I know that magnesium is in group 2. Silver, yes, I know that silver, I've memorized that, it is always a +1. Tin, nope, that's not one of the ones I memorized. So tin is going to be multiple. I don't know what its charge is. I'm going to figure it out in a second, but it could be multiple options. Copper, not one of the ones I memorized, so I don't know what that is. Potassium, always +1, it's in group 1. Zinc is always going to be my +2, I memorized that. And mercury has multiple options, so I'm not sure which one, but I'm going to figure it out in a second. So this one is going to be with calcium. I don't need any Roman numerals if it is only one. Everything in this column here, I don't need any Roman numerals with this. This is calcium bromide. This one is magnesium oxide. Here, silver nitride. And now we've got tin. Well, I know it's going to be tin, but what's my Roman numeral? My Roman numeral I can decipher, I can figure out by looking at the chloride ion. I need 2 of them. I know chloride is always a -1. If I need 2 of them, the tin must be a +2, so I use my Roman numeral of 2 to make sure I tell everybody which tin ion it is, and then it's chloride. And copper, don't know which one yet. Fluoride, the fluoride ion is always a -1 as well. Since I need 2 of them here, it must be also copper 2 fluoride. Potassium, always a +1. I don't need Roman numerals. Potassium, this is phosphide. And zinc is always a +2, so I don't have to use a Roman numeral. Remember, zinc is that one right up here. It's right as part of these 3 diagonal ones right here. 3, 2, 1. So this is going to be zinc nitride. No Roman numeral necessary, because zinc and nitrogen are always going to combine in a 3:2 ratio. Always, always, always. We don't need any Roman numeral. We don't need any prefixes. Zinc nitride is always Zn3N2. Mercury, multiple options. Well, oxygen is always a -2. I memorized that. So this is a 1:1 ratio. So the mercury must be a 2. So mercury 2 oxide. Okay? All right. Let's look at just one little extra component to all of this. There are some more of a traditional naming system. We use Roman numerals. Okay, Roman numerals is kind of now the easier accepted method, but there was an earlier, more traditional method, and that would be by changing the ending of the metal itself. By changing the ending of the metal name, we would then identify if it is, which ion it is. Okay, so I'm just going to kind of brush over this. It's not as crucial. So you'll notice here that these are metals that form only one ion. This we've already talked about, and those are all set. Nothing changes here. But the more traditional, older way to name ionic compounds with metals that form multiple ions is to change the ending of the metal itself. Okay? Instead of saying copper 1, this would be copper 1 by the way, instead of saying copper 1 oxide, you would say cuprous. Instead of saying copper 2 oxide, you would say cupric. So the OUS is for the one that has the lower charge on it, and the IC, the RIC ending, is for the one that has a higher charge on it. Okay, so this is tin. Instead of saying tin, this would be tin 2. You use more of the Latin root, by the way. So this is stannous. So instead of tin 2 fluoride, you would say it's stannous fluoride. Instead of tin 4 fluoride, you would say it is stannic because it has a higher charge on it. Okay, so that's really all I'm going to say about that. You can read through this here and answer all these questions, and you'll see how these are named down here, where instead of saying copper 2, you would say cupric. Instead of saying copper 1, you'd say cuprous. Instead of saying iron 3, you'd say ferric. Iron 2 is ferrous. Tin 4 is stannic. Tin 2 is stannous. Plum, that's for your lead, again based upon I think the Latin roots here. So this would be lead 4 is your plumic, and then plumbus is your for the lead 2. Okay, so a little bit different ending. I don't think it's going to be quite as common now that we're using the Roman numeral system. All right, and you can try these here using these endings. Again, notice what they're asking you to do is first identify if it is just have one ion for the metal or if it has multiple ones, and then use it more of a traditional name if it does have multiple ones. And here's your cheat sheet right here. Okay, that's your cheat sheet. And here you can, if you see these new type of naming system, the new type of naming system for the ones that are multiple, there it is, appears right there. Stannic, here it is with the Roman numeral. Okay, here it is with the little bit of a different ending for the metal. And here aluminum and lithium don't have any multiple ones, so it's just using the element name there. Okay. Question number 29, if you want to talk about that, all that's doing is helping you think about the flow of naming these compounds. First thing you obviously have to do is you want to identify if it is ionic. And how do you do that? It always is going to have a metal and a non-metal. Okay? That's the first thing you wanted to figure out. Is it ionic? Then you would figure out, is the metal have only one ion? One ion for the metal? Or does that metal have multiple ions? Okay? Then you can use your system. Here you could use the Roman numerals, or you could use the more traditional, older version of changing the ending of your metal to ic or us. If it only has one, then you don't have to worry about any Roman numerals. And then you remember that you always change the non-metal. The non-metal ion always is going to end in IDE. Okay? Metal always goes first, by the way. Don't forget, metal in the name and in the formula, metal, then non-metal. Okay? Always. Very important. All right. I hope that is helpful. And this is all about naming ionic compounds. Well, compounds are not only ionic. There are other types of compounds as well. So stay tuned, and we're going to continue to talk about naming compounds. In the next video, we're going to be looking at naming ionic compounds, but the non-metal part is going to be a little more complicated. It's going to be a little more involved. It's going to be a polyatomic ion. So I'll see you then.